the other immigrants. You get me, right? She was
Oh.
like, no. I mean, she's a woman and she's in this man's car.
Where was it? Here.
Yeah,
You get me right. I mean, Chileans, Bolivians, the other immigrants.
The other immigrants, you get me right?
dark-
Like, of course, like she's like black hair, white, blue eyes.
It's horrible.
Horrible, horrible.
I would get off the
Of
car
course, she
immediately.
Yeah, I mean, yeah, of course, she didn't get it. I mean, she understood what she meant, but she was not with it.
Of course.
Yeah.
No. Horrible.
That's international side.
Yeah.
Yeah.
Yeah, but that is it. Bueno, empezamos como quieran.
Oh, still 5 minutes.
Bueno, buenas tardes a todos. Bienvenidos a una nueva edición de los Coloquios IB. Este año venimos muy bien, muchos coloquios, buena participación. Así que bueno, esperamos que seamos así todo el año. Recuerden siempre que tienen la posibilidad de proponer coloquios, ¿sí? Sobre todo para la segunda parte del año, que ya estamos armando la grilla, así que siempre que tengan alguna persona en mente, argentino, pues mejor, más fácil de traerlo, digamos. Pero bueno, siempre es bienvenido las sugerencias para ir armando la grilla de coloquios. Bueno, hoy tenemos el gusto de presentar a Reinhold, ¿sí? Que es profesor invitado del programa Maldacena. ¿Sí? Invitamos a Karen a que ella lo presente. Gracias, Karen.
Muchas gracias, Julián. Hola, buenas tardes. Bueno, I'll continue in English. So it's a great pleasure to introduce you to Professor Reinhold Egger. I know Reinhold for many years already. Reinhold Egger is a full professor at the Universitaet Duesseldorf in Germany. And he visited us already in 2000 and the year 2000 and 2001. During the summer, a couple of months in each time, so from January to March. And that was very useful for us, not only a pleasure, but it was also useful because he brought the topic of graphene, and he gave a couple of courses, so it was interesting also for students. So it was, we started collaborations with Reinhold and other people in our group, which is the group of condensed matter theory here at the Atomic Center. So Reinhold is also, apart from being full professor in Düsseldorf, he is working on different topics, correlated electrons, topics on superconductivity in topological systems, thinking about quantum information processing, also electronic and magnetic properties in non-trivial topological systems, etc. So today we will hear one of his recent topics that has to do with superconducting diodes. I insist again, he was also invited by the Maldacena program, which invites distinguished professors, so we're very happy to have been able to invite you also with this program. And Reinhold, it's a pleasure again, so thank you very much for being here, and the floor is yours.
So it's a great pleasure to be here in Bariloche after such a long time. It seems like I'm always coming in times of crisis, and it has been subtly suggested there might be some correlation, but I think there is no correlation between the crisis and my stays here. But in any case, today I want to tell you a bit about a rather recent topic of interest, which is superconducting diodes. And we will first go through a brief reminder of what are diodes in general, diode effects. And I will then describe what is the superconducting diode effect. and remind you of Josephson effects in case you have never heard that. It will be a brief introduction to Josephson effects, and also the so-called anomalous Josephson effect. And then we will go into a concrete model that allows us to actually compute efficiencies and things like this for the superconducting diode effect, namely a Josephson junction where you have a finite Cooper pair momentum. Yeah? And we will discuss then the current-biased Josephson diode and the voltage-biased Josephson diode, where we will see that we get a very, very good rectification. And if you have questions, just interrupt me at any point. Yeah? Okay, so diodes are examples of non-reciprocal or asymmetric interactions or responses. We all know this from daily life, non-reciprocal feelings or asymmetric response in politics. Yeah, you know what I'm talking about. Or in technology, a one-way semi-transparent mirror. It's so common that you don't think about it, but if you think of the laws of physics, the elementary laws of physics are all symmetric under particle exchange. Yeah? Actio is reactio in Newton's laws. The laws of strong and weak forces, electromagnetic forces, they're all symmetric under particle exchange. So this is really a many-body phenomenon, and one has to think about when can this happen at all, this non-reciprocal behavior. And the perhaps most important example in technology for such an effect is the semiconductor diode that is implemented in all of our computers and has really revolutionized our lives since its invention in the 1940s and 1950s. So the hallmark of the semiconductor diode is that it has a resistance or resistivity that is depending on the direction of the current. Yeah? So you see here the resistance depends on whether you have minus I or plus I. And a schematic picture is shown here, the IV characteristic. In the forward direction, you have a small resistance. In the backward direction, you have a high resistance. If it's an ideal diode, the resistance is infinite in the backward direction. There's no current in this direction, but a large current in the forward direction. Yeah? And so this is a resistive or dissipative rectification mechanism. It comes with dissipation, so there's heat, and so on. So if we study this in a bit more detail, you see here is an example for this PN junction diode. So you take a semiconductor, one half is N-type, so it's doped with electrons, and here it's a P-type silicon semiconductor, and there's an interface in between. And what you measure then is, in the forward region, you get a large current up to some breakdown voltage, and in the backward direction, the current is very small. There's just a reverse current leakage up to a breakdown voltage, then it can suddenly sort of drop off to very large values. So the question is, why does this work? And a key requirement for all non-reciprocal phenomena is that you have broken inversion symmetry. Yeah, that's really necessary. And what happens in this charge, in this PN junction, is that from the N-doped region, electrons migrate or diffuse into the P-doped region, and vice versa, from the P-doped regions, holes diffuse into the N-doped region. But they cannot diffuse arbitrarily far away from each other because there are Coulomb forces between them. So they will be held together by these Coulomb forces, and these create an electric field in the interface. Yeah? So in the interface, you will have an electric field in this direction, and this represents a barrier. And now it depends whether you apply the electric field from the outside, so the voltage, parallel or anti-parallel to this interface electric field. If it's anti-parallel, you can lower this barrier and basically get a high current, so good transport. If it's parallel, then you have bad transport. Yeah? So in a sense, the current direction changes the depletion layer thickness, and this gives this asymmetric resistivity. And interactions are the key here, Coulomb interactions. In general, inversion symmetry breaking is a necessary but not sufficient criterion. Let me give you an example for a system that has inversion symmetry breaking but no rectification. This will be a non-interacting NIN junction, so we have a normal metal, in between there is an insulating piece. We can discuss this in the one-dimensional limit. Just take a one-dimensional Schrödinger equation. This barrier is a potential U of x that is asymmetric, so U of minus x is different from U of x. And so you have broken inversion symmetry. Since this is a non-interacting Fermi gas, you can now use the Landauer-Büttiger approach. That's a scattering theory. You just construct scattering states, and then based on the transmission amplitudes of these states, you can write down what is the current or the conductance. So this is all contained in the so-called scattering or S matrix. And so what you do is you consider a particle, an electron coming in from the left side, a plane wave, which can be transmitted with a transmission amplitude T, or it can be reflected with a reflection amplitude R. Yeah? Likewise, you can consider an incoming particle from the right side. It can be transmitted with T tilde, or reflected with amplitude R tilde. In general, these are all complex numbers. Yeah? But now, in the absence or in the presence of time reversal symmetry, meaning there is no magnetic field, then you have time reversal symmetry. There is a theorem, the S matrix must be symmetric. So S must be equal its transpose. That directly means that T tilde must be equal T. So the transmission in this direction and the transmission in this direction must be equal. So if you have time reversal symmetry, it doesn't help you that you have an asymmetric potential barrier. You will still have symmetric transmission coefficients, and the current from the Landauer-Büttiger formula will not give you rectification. Yeah? So this is the simple message. You need to break also time reversal symmetry. So that is the first key message. A non-reciprocal current response is often, but not always, found if you break both time reversal symmetry and inversion symmetry. Yeah? So these are key requirements, and time reversal you can break by, for instance, a magnetic field. Or you can break it spontaneously by interaction effects. They can also do the job, like in the p-n junction diode, where time reversal symmetry is not broken in equilibrium, but with the interactions you break it out of equilibrium. So once you have diodes, you can play a lot of games. Engineers know that. You can build a rectifier, for instance. You can convert an alternating current or alternating voltage, shown here. With time, you have positive and negative, positive, and so on. If you have an ideal diode, it will just chop off the negative voltage pieces, and you arrive at this. If you average this over time, it's a directed voltage, or you can do the same with a current. Yeah? You can convert AC current into DC current. And such a thing is called a rectifier. So that's the background, the normal p-n junction diode or normal semiconductor diode. And here I want to ask and address two questions. The question number one is there a diode effect for supercurrents? So for dissipation-less superconducting diodes. And we will first consider the equilibrium case without a voltage, where you, for instance, impose a fixed phase difference across the ends of the superconductor. This is called the superconducting diode effect. And remarkably enough, this has only been discovered experimentally 3 or 4 years ago. So it's really a very recent development. And in the last part of the presentation, I will discuss what happens if you drive this system out of equilibrium, so if you really have a dissipative diode. And we will see that this gives an even better rectification mechanism than the first one. So to start, let me remind you of the famous Josephson relations. These were found by Brian Josephson while he was doing a PhD in, I think, in the early 60s. His supervisor was John Bardeen, a double Nobel laureate, so he had 2 Nobel Prizes already. And Brian Josephson suggested these relations, and John Bardeen said, it cannot be, it's wrong. But Josephson went ahead and published, and 1 year later the experiments showed he was right. So sometimes a PhD student can be right, even though the advisor tells him, no. But that's a rare case. I mean, usually the advisor is right, I should say. Yeah. So in this case, what Josephson considered were 2 superconductors, these blue pieces here. And in what I'm telling here, I will just look at S-wave BCS superconductors. So they're described by a so-called mean field theory, in which you have Cooper pairs as the essential ingredients, plus quasiparticles. So the elements of a superconductor are these Cooper pairs formed by spin-up and spin-down electrons. They form a bound state with opposite momenta, and this bound state effectively is a boson. It can condense. So it forms a Bose-Einstein condensate, but it has charge, 2e. And that's why it can give you a supercurrent. It can give you a current that flows without any dissipation, without any resistance. On top, at finite temperature in superconductors, you also have the possibility to have quasiparticles. So single fermion or hole-like particles that obey Fermi statistics, but they have a gap. And this gap is related to the order parameter, the absolute value of the order parameter of these Cooper pairs. Yeah? And the order parameter describing these Cooper pairs also has a phase. It's a complex number. And so Josephson considered this case that you have a fixed phase difference between these phases of the order parameter. And there's a tunnel barrier, a tunneling contact of amplitude lambda in between these 2 superconductors. Now what he showed was that to lowest order in lambda in this weak tunneling amplitude, you can get a tunneling of Cooper pairs, which gives rise to a coupling energy that goes like minus Ej cos phi. It's periodic, 2-pi periodic in this phase difference phi, and the Josephson coupling here is proportional to lambda square because you have to transfer 2 electrons. Cooper pairs made of 2 electrons. And now in equilibrium, the phase derivative of the free energy gives you a current. So Josephson realized that by taking the derivative of the free energy, and especially this term here, you get a current phase relation. So depending on this phase difference, there will be a supercurrent flowing, which is given by a critical current IC times sine phi. It's a quite universal relation. It doesn't depend on the materials. Material properties or the properties of this weak link, they're all hidden in the scale IC, in the critical current. And this critical current is the maximal supercurrent the junction can carry. Yeah? If you drive a bigger current through this junction, it must be carried by quasiparticles. But if it's smaller than IC, then you can have a pure supercurrent. So it has no resistance, very different from the current in a normal metal. So Josephson also specified a second relation, and these 2 relations together earned him a Nobel Prize. So the second Josephson relation refers to the case that you apply a constant bias voltage V. So in a constant bias voltage V, he specified that this phase should have a time dependence with a Josephson frequency given by the charge of the Cooper pair, 2e, divided by h bar, so these are natural constants, times the voltage. Super universal, doesn't depend on anything, doesn't depend on the materials, on the interface, on whatever. This is really super universal. The first Josephson relation is much less universal. It holds only in the deep tunneling limit. So only if it's a weak link, if this is almost opaque, in general you can expect a non-sinusoidal current phase relation. And we will see these deviations from sinusoidal current phase relations are very important in understanding superconducting diodes. For instance, if you have a single channel Josephson junction with a transmission probability tau, so this tau is between 0 and 1. If it's close to 0, that means that you will have a very weak contact. If it's equal to 1, we speak of the ballistic limit. Then the channel is open, you get the maximum supercurrent. So that's the formula you get, and you see if tau is very small, the denominator here is just equal to 1. You are back to I is proportional to sine phi. That's the Josephson relation. But if tau becomes sizable, approaches 1, you get strong deviations from sine phi, and it's a non-sinusoidal current phase relation. So now we are ready to say what is a superconducting diode. A superconducting diode is a system that can support a supercurrent flow in one direction, while in the other direction it is a resistive current. Yeah? So only in one direction you have a supercurrent flowing with 0 resistance. In the other direction, you have a finite resistance. So meaning there is no supercurrent, but it is quasi-particles that flow. It's clear that in order to have this effect, what you need is that the critical currents depend on the direction. So there must be a critical current IC plus for the plus direction and a critical current for the minus direction, and they need to be different. If they're equal, you will not have this diode effect. So if they're different, then that opens a window between these two. And if the current that you impose to flow is in between these two, then if it's flowing, for instance, if the critical current in the minus direction is bigger, then if this current flows to the minus direction, then it can flow as a supercurrent. But in the opposite direction, it can only flow as a resistive current. Yeah? So that's the basic effect. And a typical toy model for that is a skewed Josephson junction for skewed superconductors. So you have gaps delta plus and delta minus that are different. And delta plus is for right movers. Delta minus is the pairing gap from left movers. And then these are quasi-particle branches, and here is the supercurrent branch, and you get different currents for the plus and minus direction. So then one introduces an efficiency parameter to characterize how good such a superconducting diode performs, which is this eta naught, and it's defined as the difference of the critical currents divided by their sum. Yeah, and then take the absolute value. If both currents are equal, then of course this is 0, it's not a diode. The maximal value this efficiency can have is 1, in which case, for instance, IC plus is 0. This would be this case. A current flowing in the plus direction, in that case, is always resistive. But in the minus direction, as long as the voltage is below this breakdown voltage, it's always a pure supercurrent. Yeah? So that is the ideal case in this situation. So now let me flash the first experiment that reported the superconducting diode effect. This was in a bulk superconductor, not a Josephson junction, but really a bulk superconductor. This was done in 2020 in a Japanese group led by Teruo Ono. And they studied a Rashba superconductor built in an artificial superlattice. So the superlattice is here made by stacking tantalum, niobium, and vanadium layers. And it's a non-centrosymmetric arrangement, so you break inversion symmetry. You also apply a magnetic field in this layer direction, so you break time reversal symmetry. And this specific structure is designed to maximize the so-called Rashba spin-orbit coupling. Yeah, the Rashba spin-orbit coupling is a specific type of spin-orbit coupling that corresponds to an electric field along this direction. Yeah? And then it couples the orbital momentum of electrons to its spins. Okay, so what they then observed is that if they have the magnetic field, say, in this direction, the spin-orbit field is in this direction, so perpendicular, and if the current is also perpendicular, so in this direction it will flow as a supercurrent carried by Cooper pairs. In the opposite direction, it can only be carried by quasi-particles and comes with a resistance. So this is shown in this plot here. First in the, oops, what was that? Sorry. I have to flash. Okay, so here we see in the left panel, by raising temperature above about 4.5 Kelvin, the thing jumps to the normal state. So the normal state resistance is about 4 ohm in this device. Below that temperature, it's a superconductor. Yeah? And now they look at the case that they apply, for instance, a constant current of 6.6 milliampere and alternate the magnetic field direction. They apply 0.02 Tesla, a very small field, and then always change the direction of the magnetic field. So look at the red curve. So here you see it's zero resistance, so it's a supercurrent flowing if the field is in the plus direction and the current is also in the plus direction. Now you reverse the magnetic field, the resistance jumps to the normal state resistance, 4 ohm. You reverse it again, it goes down again to the superconducting, to the supercurrent, so zero resistance and so on. And if you take the opposite value of the current, then you exactly reverse the whole pattern. Yeah? So this is a reversible switch between a supercurrent and a resistive current in such a superconducting diode. And the picture is again shown here. The supercurrent is carried by the Cooper pairs, so basically 2 married electrons that form a bound state and then can flow in a dissipation-less manner, while in the opposite direction it's carried by single quasi-particles. Okay? A very similar experiment is shown here. I should say since 2020 this field has exploded. There are now many, many experiments. If you look on the archive server, almost every day new realizations, new materials, new effects are shown, and also new theories, of course. So it's a very hot field, and this example here is a niobium telluride Josephson junction. It's an experiment done in the group of Stuart Parkin in Halle in Germany. And they did a very similar experiment, in that case keeping the magnetic field constant, the direction constant, but alternating the current direction. So here, as a function of time, you see that the current is alternating, and the red curve is the resistance. So you see the resistance jumps between 0 and the normal value, the normal state resistance. 0, normal state, 0, normal state. It's exactly as the example before, so you can see it either in bulk superconductors or in Josephson junctions. And we will come back to this experiment a little later again. So how about theory? Was this predicted? Yes, it was. And the first, to my knowledge, who pointed out that this effect should be there was Edelstein in '96. So almost 30 years ago. He studied the Ginzburg-Landau equation. Ginzburg-Landau theory is essentially equivalent to BCS theory. He studied that for a polar superconductor. So polar meaning there is it's like a stacked material. There's a polar axis that defines a Rashba spin orbit term. So the Rashba spin orbit term is shown here. It couples orbital momentum or momentum to the spin, and this axis C is this polar axis here. Yeah? So there's a Rashba spin orbit coupling. There is an in-plane magnetic field, and he studied a current direction, for instance, perpendicular to all these three. And from his analysis of this Ginzburg-Landau theory, he found that the critical current density is given by this expression, and the important term is this term here, so you can ignore this is just a constant. C cross B, B is the magnetic field, dot J. J hat is the direction of the current. So if this is perpendicular both on B and the polar axis, it's maximal. Yeah, that's the best case, and B should be perpendicular on C. Then you have the biggest effect. But now you see if J is in the plus direction or in the minus direction makes a difference, because then this term will differ in sign. So if a current is in between these two values, that predicted by this formula, you will have the superconducting diode effect. In one direction, the current is carried by Cooper pairs, in the other, it is carried by quasiparticles. Yeah? So this was really the first prediction. Back then, people didn't take it very seriously. You see, it appeared in Journal of Physics Condensed Matter, not one of the top journals, but it wasn't cited very much. Now it's cited very, very well. Yeah? But he was really the first to see this effect. So these type of effects are very closely related to the so-called anomalous Josephson effect. So let me come back to the Josephson effect. So we have two superconductors separated by an insulating barrier. And you can now prove that if you have either time reversal symmetry or inversion symmetry, or both, then the current phase relation must always be odd under phase reversal. Yeah? So in other words, if you change phi to minus phi, the current must change its sign too. That directly implies that for zero phase gradient, for zero phase difference, the current must vanish. And that also means you can expand this as a sine, a harmonic series of sine functions. One might naively think that this is always the case, but it's not. If both these symmetries, time reversal and inversion symmetry, are broken, you may find the anomalous Josephson effect, namely a finite supercurrent flows even at zero phase difference, and you have a more complicated current phase relation that doesn't satisfy this relation anymore. So in the tunnel junction limit, basically, if that happens, of course, you need also cosine components in the harmonic series. In the tunnel junction limit, it turns out only the lowest components are important, so you have a sine of phi and a cosine of phi component. And if you know your addition theorems of sines and cosines, you know that you can combine them to a sine of phi plus some shift. Yeah? So that means in the tunnel junction limit, if the barrier is very high here, you will get a standard Josephson relation, but with this shift, if both these symmetries are broken. This is a possibility, and one calls this the anomalous phase shift. Yeah, so that's the phi naught junction. This is interesting, but it doesn't give you a superconducting diode, because you see from this current phase relation, the maximal current in the plus direction is IC, and the maximal current in the opposite direction is also IC. So there is no way you can rectify a supercurrent here. So this already tells us the superconducting diode must go beyond this deep tunnel limit. You have to have a sort of more transparent junction. And in fact, the best way is to have a fully open junction. Yeah? Then the superconducting diode effect is always maximized. This anomalous Josephson effect has also been observed experimentally in very beautiful experiments done in Delft in the group of Leo Kauvenhoven in 2016. So here you see a squid geometry with a niobium titanate as a superconductor. And here there is an indium antimonide nanowire, and here is the weak link, so to speak. And in the weak link, you have a quantum dot. And this quantum dot, in that case, had effectively two levels. You need at least two, otherwise spin orbit doesn't do anything. Indium antimonide has a very strong spin-orbit coupling, so you have a strong spin-orbit coupling in this interface region, and there was an in-plane magnetic field. Tunable, you could rotate it in this plane, and you can now measure the voltage across the squid versus the flux the magnetic flux that pierces the squid at a constant current, and that gives you information about the current phase relation. So you can directly measure this current phase relation. And what they see is indeed that the current phase relation has this phi naught shift. And the phi naught shift was completely in accord with theory. So because theory made special or very precise predictions on how this should vary with the magnetic field direction, and this was all nicely observed in these experiments, and there were also later experiments that fully confirmed this effect. But we have to see now how we can explain the superconducting diode, and an easy way to see necessary and sufficient criteria is to include the lowest few harmonics of the current phase relation. Yeah? So if we are close to the tunneling limit, we can truncate these series at some order, and the lowest terms are the following. So the first one is the one that Josephson wrote down. The next correction would be effects beyond the tunneling limit, basically tunneling of two Cooper pairs. That's this B2 term. And the effect due to the anomalous Josephson effect is contained in the lowest harmonic of the cosine. So let's call this A1 and this B2. And now this is a simple exercise. Find the maximum and the minimum of this curve for phi in one fundamental interval. Yeah? And the answer will give you IC plus and IC minus, and this difference determines your diode efficiency. And what you find from this simple calculation is this is proportional to the product of A1 and B2. So in other words, in order to have the superconducting diode effect, both A1 and B2 have to be different from zero. Yeah? So you have to have the anomalous Josephson effect, and you have to be away from the tunnel limit. Then it will generically happen, this diode effect will generically happen. And this was predicted by us in a sequence of papers already way before people discovered this, and the Bariloche group also had similar results. I will comment on that in a few minutes. So this will now be the model that we will look at for describing in a more quantitative manner the effect of a superconducting diode. So we will consider that the superconductors in question on the left side and on the right side of a Josephson junction, so this is the junction, have a finite Cooper pair momentum. That means this finite Cooper pair momentum means that you have an oscillatory order parameter, and in between there is this short weak link. Yeah, this is a model that we will see can describe even experiments. So a finite Cooper pair momentum is in fact interesting because we know that if you have a superconductor that has a finite a ground state with a finite Cooper pair momentum, then this is basically sufficient for obtaining this diode effect. It's not necessary, meaning there are also other mechanisms that could give this effect, but it's sufficient. The almost means you have to be away from the deep tunneling limit. Okay, so this state will directly break time reversal symmetry and break inversion symmetry, so these typical requirements are directly fulfilled. The question is, how can we get such a state in nature? So what are the recipes to generate ground state of a superconductor that has finite Cooper pair momentum. I'm aware of 3 routes to do such a task. The first one is the Fulde-Ferrel state, which was explored in the 1960s by Peter Fulde and Ferrel. And that is a state where you consider a clean superconductor in an in-plane magnetic field, a Seemann field, and without spin orbit, and the BCS mean field equations in a certain field range then predict that there should be a ground state that has a finite Q. Yeah? But the solutions can be either plus Q or minus Q. There are always pairs of solutions, and the Fulde-Ferrel state invokes a spontaneous symmetry breaking. So there must be some spontaneous symmetry breaking. You pick either the plus or the minus Q state, and then you have a state that would give you a superconducting diode. It has been very hard to find this Fulde-Ferrel state in experiments. To my knowledge, only in 2007 in heavy fermion superconductors it has been seen, and the problem is that this effect is very easily destroyed by disorder. So if there are impurities in your material, it can easily kill the effect, and to my knowledge, the superconducting diode effect hasn't been seen using this Fulde-Ferrel route. What people, almost all the experiments have done is follow this route, what I would call a helical superconductor or magnetochiral anisotropy, and that's really what Edelstein advocated, namely the interplay of spin-orbit coupling and Seemann field, which can generate this effective Cooper pair momentum. This was also pioneered in an important paper by the Bariloche group here in 2008. We did that for the Josephson junctions, and the group of Liang Fu also looked at it again lately. So that is basically the most important route, I think, because it is robust against disorder. It can tolerate disorder, so in practice this is robust and works. And then finally we have the possibility that we have heterostructures of superconductors and ferromagnets. So in a ferromagnet, when the ferromagnetic order leaks into the superconductor, you can also generate a Fulde-Ferrel-like state, and this could in principle also give rise to a superconducting diode effect. So whatever the origin of this finite Q, let's write the Q as 2 times small q and assume it to be identical on both sides. Also the pairing gap is assumed identical, and we assume that the junction is just a short link with transmission probability tau. This is the model that was suggested by Liang Fu's group to describe the experiments of Stuart Parkin's group. Yeah, we will see that it fits these experiments quite nicely. So in that case, the superconductor is described by a one-dimensional so-called Bogolyubov-de Gennes Hamiltonian, and another one here, and there's a weak link, and at the end here, the state at this end and the state at this end are matched by a matching condition. Yeah? What you do in quantum mechanics basic courses, matching 2 states together, and this matching condition depends on the transmission probability of this weak link tau. Later you will also see psi. This is the superconducting coherence length, which is Fermi velocity divided by the pairing gap, and this is roughly speaking the size of the Cooper pair. So in this model, one finds that if you gauge away this oscillatory factor, you find a Doppler shift. Yeah? So one finds that the quasi-particle dispersion here has different spectral gaps for right and left movers. So these are exactly Doppler shifts, Doppler shifts that result from the finite Cooper pair momentum, delta plus or minus VFQ. Yeah? So these are the 2 gaps that appear in this model. And here is this experiment that I was referring to, Stuart Parkin. So this was interpreted using exactly this model. And in the experiment, so here you have a niobium telluride Josephson junction and a magnetic field in plane, and you find the supercurrent can be sort of unidirectional as shown here. And what they found is an efficiency of up to 40%. So it's a pretty large Josephson diode effect. And this model with a finite Cooper pair momentum seemingly explained all the main observations. Yeah, that's why, even though the model is rather simplistic, it can even describe a complicated experiment like this experiment here. So in this model, you have different spectral regimes for quasiparticles of energy E, because we have two gaps. If the energy is below both gaps, you wouldn't expect any states, but of course, because of the weak link, there could be localized states near the weak link. Yeah? So bound states that are localized exponentially close to x equals 0. That's where the link is. In superconductors, these bound states are special. They're called Andreev bound states, and they're special because they can carry a supercurrent. Even though these are localized states, they carry a supercurrent because their energy depends on the phase difference. And remember, the supercurrent is the derivative of the energy with respect to phase, and that generates a current. Yeah, so these bound states, in fact, carry the most of the supercurrent in these Josephson junctions. Then above both gaps, you have the usual propagating continuum, quasiparticles, fermions, or holes in both directions. And there's an intermediate regime between both gaps where you have mixed character states. They are propagating in one direction, they are decaying in the other. The good news is that in our theory, we can unify all three regimes and by analytic continuation, write down the eigenstates in all three regimes. Here I just show you the Andreev bound states that depend on phi, on the phase difference across the junction. And you can write down analytical results in this ballistic case. So tau is 1, the channel is fully open. That's the most advantageous case for the superconducting diode. So this, the dispersion relation of the Andreev bound states, there are two branches, plus or minus, blue or red. And you see it's a cosine of phi half, not cosine of phi like in the Josephson relation, but phi half, and that's because we are in the ballistic case. And there's a shift, so the energies are shifted in energy, yeah, by Q times the superconducting coherence length. So this is a dimensionless number. Q parameterizes our Cooper pair momentum. So here you see the standard result without a finite Cooper pair momentum. And so there are two branches, and what you get when you add a finite Cooper pair momentum, one of them shifts up, the other shifts down. Yeah? And now given these results, it's a relatively simple matter to compute the current phase relation. You also need to compute the contribution from the continuum, which doesn't vanish here. Turns out it's just a constant in this case, and once you have that, you again maximize and minimize the current phase relation to get the maximum and minimum supercurrent. And from that, you get a simple formula for our efficiency, which is written down here as a function of Cooper pair momentum. Yeah, that's a zero temperature expression. If you now maximize this with respect to the Cooper pair momentum, you find that around 0.9 for Q, it has a maximum of around 40%. It's exactly the value they saw in the experiment. Yeah? And the plot is shown here. So for tau equal 1, this is an analytical solution. As a function of the Cooper pair momentum, Q, you see eta naught, the efficiency. So it's this curve, the bigger up to 0.9, here you have 40%, and then it goes down again. And you see also that if you now make the transmission slightly imperfect, you just go to 0.99, 99%, you would think this is still very, very good. You already diminish the eta naught, the efficiency, to 30%. If you go down to 0.9, it's below 20%. And of course, in the deep tunneling limit, it's 0 as expected. Yeah? So we see a rapid decrease of the efficiency as the transmission gets lower, and there's an optimal working point at a Q of around 0.9, and that's independent of tau. Yeah? This seems basically always around this point. You have a maximum, and if we sit ourselves at this maximum and now look at eta naught as a function of temperature in units of the gap, we see that raising the temperature will also decrease this efficiency quite rapidly. So you need to be at low temperatures and open junctions, then you can see a very efficient diode behavior. We've also done a numerical simulation of an alternative model where the superconductors are just S-wave with 0 momentum, 0 Cooper pair momentum, but we put the Zeeman field and the magnetic field into the barrier. So we have a quantum dot in the barrier, very much like this Kauvenhoven experiment for observing the finite junction effect. And in this model, in this parameter regime, there are effectively 2 levels of this quantum dot inside the pairing gap. And we include spin-orbit coupling alpha naught. We include a Zeeman field in plane and a dot potential. So by gate voltages, you can tune this this potential mu. And here in a color scale plot, you see in the plane spin-orbit coupling versus this dot potential. The color scale gives you the efficiency of the superconducting diode. You see on these lines, here there is a sizable efficiency. Here this plot shows you a cut at the line alpha equal 1.4. So this peak is this, and this peak is this one. And at this peak, you have a 25% efficiency, and the corresponding current phase relation is shown here. You see it's strongly non-sinusoidal, and so you get similar values, 25% or 40%. So that's the typical range that you can expect in these type of systems. But what's important, these black lines here, they give you the positions of resonances where many-body energy levels cross 0. And at these points, you have a very high transmission. Yeah? So whenever there is a resonance of energies, you typically get a high junction transparency, and so we have the same qualitative conclusions as from the other model. To have this superconducting diode effect, you need spin-orbit coupling, Zeeman field with the appropriate directions, and a high junction transparency. So the last few minutes, I want to talk about the voltage-biased case. So when we apply, if we not just keep the phase difference fixed, but we apply a finite constant bias voltage. In that case, the analysis is a bit more difficult. You have to work with a Landauer-Büttiker scattering approach. So you consider incoming plane waves and 4 different types of incoming quasi-particle states. So here on the left side, you see the spectrum of our superconductor with finite Cooper pair momentum. You have 2 gaps, delta plus and delta minus, and of course the whole thing also has a negative branch, minus delta minus and minus delta plus, and there are electron or hole type branches in the spectrum. We have one Fermi point at plus kF and the other at minus kF. So there are electrons, so at a given energy, there are electron-like states that move to the right or to the left, and likewise for holes. So there are 4 types of incoming states. Now consider, for instance, an electron that sits, let's say, at this energy. So it's of type 1. So it's injected from the left side. So this is the left superconductor. Here there is the gap. So there's a gap for single particles between minus delta minus and plus delta plus. In the ground state, all these states are occupied, all these are empty. And here there's the gap. So now when you inject this particle, this here is the interface region. Think of a normal region. So the electron can now propagate through this normal region. because the voltage drops at the interface, it will gain an energy EV. So this axis here is energy. Yeah? So it gains the energy EV. Now it hits this SN or NS interface. What can it do? It cannot go into the superconductor because there is a gap. There's no density of states for single electrons, so it can not enter as a single electron here. It could only enter up here into the continuum. So what it can do is what we call Andreev reflect. An Andreev reflection means that instead of being reflected as an electron, which it will not do in this case because we are in this case in the ballistic limit, it can be reflected as a hole. So it converts itself into a left-moving hole, but in order to do so, you have to maintain charge balance. Yeah? So the charge, the missing charge, has to go to the right side. So in effect, you create a Cooper pair at zero energy on the right side. So you create a Cooper pair here, and a hole goes to the other side. Yeah? So it moves to the left and again gains energy EV because it has charge plus E now. And here you have a second Andreev reflection. In this case, you suck out a Cooper pair from the left side and convert it, and the hole is Andreev reflected into an electron. Yeah? So this is this Andreev reflection in superconductors. So what in the end you have, once you are here, you have gained an energy of 3 EV, not electron volt, but E times the voltage. And what you have transferred is a Cooper pair and a quasi-particle. So you have transferred 3 charges, 3 elementary charges, and the system has sort of sucked up 3 EV in energy. So the outgoing state differs in energy from the incoming state by 3 EV. This is this famous Andreev reflection, and because we have multiple Andreev reflections, especially if the voltage is very small, you can imagine now that these go like this. There are many zigzags, so the ladder has many rungs, and eventually this is a ladder, and one calls this the multiple Andreev reflection ladder, MAR ladder. And you have to sum all these diagrams in order to construct the correct scattering state. So in the ballistic case, this is the only thing that can happen. If you have also back reflection, so tau less than 1, you can also have normal reflection. So the electron could also be back reflected in the barrier, and I will show you a diagram in a second. So here we see schematically again this diagram that we just saw. The electron is injected, Andreev reflected, and then enters the upper continuum. And now here at that energy, this is now the energy En, E plus NeV. For this picture, N is equal to 3. Yeah, but you could have other N's as well. You could scatter to any energy. N can also be negative. Yeah? So for a given N, you have now a set of scattering amplitudes, A, B, C, D, that tell you which states, with which amplitudes you have occupied these states. And in order to determine these, you insert your scattering state into the matching condition, and you get recurrence relations that relate all these coefficients to each other. So for different N, and you can solve them recursively on the computer. For tau equal 1, in the ballistic case, you can even solve it analytically. Yeah? Here, the promised example for a process with normal reflection. So first you have Andreev reflection, another Andreev reflection, and here you put the barrier in the middle of this normal region. There's the back reflection, and you see an incoming electron is back reflected in that case. So that would be a MAR process supplemented with a normal reflection event. So as I said, in the open limit, so in the ballistic limit with tau equal 1, we are in the fortunate situation that we can resum these recurrence relations and get a complete and exact analytic solution for the current voltage relation of the device in the presence of a finite Cooper pair momentum. And the solution is very simple. It is the sum of two terms. The first term is the result that you would get if Q is 0. And then there is a finite shift. And this shift is exactly the current carried by the Cooper pairs with finite Cooper pair momentum. Yeah? And the first term here was already computed 30 years ago in a famous paper by Averin and Bardas. So that's the analytical solution in the ballistic limit for the standard case. It's written as an integral representation. I don't bother you with that. Just give you the two limits. In the limit of large voltage compared to the gap, you effectively get the IV of a normal conducting channel. Yeah? Then it's an open channel has a conductance 2e squared over h. And so that's what you get from this solution, while in the limit of very small voltage, what you can do is you can take these Andreev levels that I showed you before in the ballistic case, and the small voltage means now that you traverse these Andreev levels very slowly, adiabatically basically. And at the time averaged Andreev level current, by time averaging this, you find it's a constant current, only its sign depends on whether the voltage is positive or negative. So it's a very simple result. And with this, we can now look at the efficiency for rectification of this diode. And now, of course, it's a resistive rectification because we always have quasi-particles in the game. So in this MAR process, you see it's always a mixture of Cooper pairs. The Cooper pairs do the supercurrent, and so they're very efficient in carrying the current. But you always, on top of it, have at least one quasi-particle. Yeah? And so there will be a resistive contribution. And so we should use here a different convention for the efficiency, and we use the convention that is used for the PN junction. So that's the same definition what you would use for the PN junction to say what is the rectification efficiency. It's a number between 0 and 1. So in the low temperature limit, and assuming that we are in the ballistic limit with an open junction, this exact solution gives you in the limit of large voltage this result, and for very low voltage this result. Yeah? So in the large voltage limit, it might be surprising that you still get rectification, even though you are very far above the gap. You might expect the superconductivity is long killed. You are way up in energy, but it decays only like 1 over V. Yeah? So there is still some rectification left. And the prefactor, of course, the bigger this Cooper pair momentum, the bigger this effect will be. In the low voltage limit, however, this is just this number. And so as this approaches 1, that's the biggest value allowed by the theory. You approach the perfect rectification limit of 100% in the limit of low voltage and low temperature. So in contrast to the current biased case that we discussed first, where we had the limit of 40%, here we could go in principle all the way to a full rectifier of 100%. Yeah? So a one-way ideal diode. So that suggests that in experiments it might be better to work with voltage bias than with current biased junctions. Because we expect this kind of phenomenon should be quite universal and give you highly efficient resistive rectification. And again, the physics behind it is this multiple Andreev reflection that causes this effect. So let me conclude. I walked you through the basics of the superconducting diode effect, which is a very active field of interest right now. We discussed a simple model with finite Cooper pair momentum, then discussed the current biased Josephson diode and the voltage biased Josephson diode, and there we find a very efficient rectification mechanism. There are many open issues right now. It's a very active field. For instance, there could be many other reasons for generating this superconducting diode. For instance, flat bands in strongly correlated systems like twisted bilayer graphene. People have observed a very big superconducting diode effect, and it's known that there are these flat bands at magic angle twisted bilayer graphene. Or in strongly correlated systems, if you find a high temperature superconductor that shows this effect, then you're directly in technological business. You don't have to cool to very low temperatures and can get such effects. Diodes with very low power consumption because there are dissipationless currents in the game. So time will show us how many applications will be possible, but I think it's an exciting development, and I hope you enjoyed the talk, and thank you for your attention.
Thank you very much, Reinhold. Bueno, preguntas, questions?
In the equilibrium situation, just before talking about the Mars, you showed the resonances, no, this, and the oscillation along these resonances, these oscillations of the efficiency, essentially, not the color.
Oh.
Why are these oscillations? What kind of interference gives you this type of?
I'm not sure this is physics. It could be just finite resolution of the numerics. This was done by Thibaut Jonker. I would have to ask him if this is just the grid that he took. And if he goes in between, he also finds a big, but I think most likely then you would just get a, I mean, these are expensive computations, and so, but it's a good remark, yeah. The referees didn't ask us, fortunately.
The other, I mean, thing is, are you thinking of, people are thinking about applications, real applications, electronics, superconducting electronics with this type of?
Of course, people are thinking of quantum sensors, for instance, or magnetic field sensors that exploit these type of effects. This is one of the applications. Low power consumption diodes is another aspect, but I mean, the effect has been experimentally seen just 3 or 4 years ago. So right now, the task is to find the best materials, to find the best ways to produce cheap and reliable diodes of this type, and then see what you can do technologically. But of course, my interest is more in the fundamental, on the fundamental side than in the applied side.
I have a short question. Thank you. It's very basic, but if you have a finite Q superconductor, isn't that already set in a natural diode because the ground state has a finite Q in a particular direction? So in principle, you could not generate a superconductivity in the opposite direction. So what am I missing there?
Yeah, in a sense, you are right. This is already a natural preference for a supercurrent. In that sense, you are perfectly right. This is an obvious way for generating such a, in the bulk case, a superconducting diode. Yeah. Now for the Josephson diode, it's a bit more subtle.
Hello, thank you very much for your talk. I have a question, maybe not a really smart one, but when you showed us a superconductor where Cooper pairs can only flow in one direction,
yeah,
and the other way the current must be normal. In the ground state, does this superconductor always have, a current flowing through it? Like you make a ring out of this. Is it going to superconduct in one direction, or does charge accumulate because Cooper pairs go in one direction, but you cannot have resistance?
No. You have to have electrodes that suck out the current. I mean, it will not accumulate forever. Yeah, so,
okay.
Yeah.
Okay.
So there must be. I mean, for instance, in a squid like what I showed you here, in a squid geometry like this, you can easily probe this by probing the voltage at a fixed current, and then you see exactly the phase dependence of this supercurrent that flows through the weak link.
Okay, thank you.
More questions? Well, okay, we thank Reinhold again. Y nos vemos el próximo coloquio.